Okay. Let's start. Long day, huh, Victor?
It's been a long day.
We are going to start chapter 5. We're going to talk about integrals and antiderivatives.
Oh no.
Yes. I should have stayed open today. And what we're going to do now is we're going to look at solving one of the problems that I mentioned before, way back at the start of the semester, probably in the first lecture, maybe second lecture, where I spoke about the two main problems that, it's not what they're used for today, but the birth of calculus kind of came about by looking at two fundamental problems that we wanted to solve. There was the rate problem, figuring out how fast something was moving. We realized that to figure that out, we developed this thing called the derivative. So the derivative was the answer to the rate problem. The other problem was the area problem. So that's what we're going to tackle now. So-called area problem. Basically, how much space does something take up? That is the question we want to answer, right? So the derivative was the answer to the question, how fast is this thing moving, right? We want to now find the answer to how much space does this thing take up, which is an important question. You can imagine that if you own a plot of land and the government is charging you property taxes, you're going to want to know that they're charging you on the right amount of land. You can't dispute how much land you have. You have to know how much land you have. But what if your land isn't a perfect rectangle? It's this weird shape. How do you know how much land you actually have? What is the area, how much space your property is taking up? Right? That's the kind of question that we want to answer. Right? And you might have seen this before, back in high school, one way you kind of try to measure area of weird shapes. What was how you used to do it? Do you guys remember?
We used to take shapes of the area of shapes you did know and just fill it in and try to make it the best.
Yeah. And a very common thing was to do like a grid, right? You put the shape on top of this grid, right? And you cut it up, and basically the area of all these little shapes, like the area of rectangles. And then if there's a piece that's only a part of a rectangle, you kind of guess, well, that looks like a quarter of a rectangle, and you kind of approximate it, right? That's sort of the idea. That's where we're going to start. We're going to try to figure out the area problem, how to find the area of a weird shape. And we want to figure out a nice, sophisticated tool to do this. Just like how the derivative was a very nice, sophisticated tool to find the rate of change of something, we want a nice, sophisticated tool to talk about the area problem, how much space something takes up. But here's an idea. Let's say I do put this thing on a grid. What if I were to do something like this and think of it as, not just as some blob, but let's say I cut it off here, and what I can actually think of this as is just two curves, right? Here's one curve, there's a top curve. That's like my f of x, maybe. Let's say I can find a function that measures that curve. And then here's a bottom curve. That's called a g of x. So the idea is, let's figure this out by finding the area under random curves. If I can find the area under a curve, what I can do is I can create any other random area by a bunch of curves being attached together. And then I can do something like find the area under f and subtract the area under g, and it will leave me with the area in the middle, in between them. Right? So that was the first idea. So now we get to the problem of, well, how do you find the area under a curve? So the idea is to break into curves. And now you're like, well, what do we do now? Well, we kind of piggyback on exactly the same idea. So we come up with another idea. okay, we use this area, we use shapes that we know what the area looks like, so let's actually do the same thing here. We've reduced the problem to being in, like, we only have to deal with one side. So let's actually do that thing that we did before and cut it into rectangles. Right, where these guys have some sort of height. Right? And the idea is, use the area of the rectangles to approximate the area of the curve. That's the idea. Right? So we can reduce a problem of finding this, how much space something takes up, as just finding the area under curves. How do we find areas under curves? Let's just do rectangles again, right? Where if we can figure out the length and the height of each of these rectangles, add them all up, we can approximate the area under the curve. Okay? So now, there are many, I was going to say several, but there are actually many more. Many ways to do this. Formulate this. We'll cover 3 very common methods, but there are many more. So the methods are called the right-hand rule, not to be confused with the right-hand rule from physics, but the left-hand rule. It's not that right-hand rule. the other right. There's a right-hand rule in physics that tells you how, like, an electric field is.
Yeah, and you're going to turn
Yeah.
it, so going down too.
Yeah, but it's
those
not.
Are, those
it's
are
not.
so like confusing.
It's not that one. It's a different one. And there's the midpoint. So we will look at 3. That's just the start. This is just going to be the beginning of the chapter, where we're going to look at 3 elementary methods of doing this process. Taking a random curve, erecting rectangles under that curve, using the area of the rectangles to approximate the area of the curve. So if I add up the area of all these rectangles, it will give me some sort of estimate for the area under the curve itself. So that's what we're going to do. Now I'm going to describe each of these to you in principle, and then we're actually going to put it in practice. And I'm going to do some problems similar to like what you might see on a test. So let's look at the right hand. You might also see it referred to as right-hand endpoints. So they might say, use right-hand endpoints to do this. Right? So the idea is the following. Let's say you have some curve that you want to measure between, say, A and B. You want to measure the area. What you can do is how we're going to formulate it is, we're going to think of it as dissecting the x-axis between A and B into an equal number of spaces. And we say we're doing the right-hand endpoints if on each subinterval, these things that I broke it into, they're called subintervals. On each subinterval, take the right side and let that determine the height of the rectangle. So I extend up straight till I hit this curve, and then that's the height of my rectangle. Move on to the next one, take the right side, hit the curve, that's my rectangle. Next one, right side, hit the curve, that's the height of my rectangle. And we keep doing this on the right side all the time. What we say is that we're using right-hand endpoints to approximate the area under the curve. You'll notice here that in this case, right, not always would the right hand do this. But you can clearly see this is an overestimate of the area. Notice that the rectangles cover the entire curve plus more. Right? So if I measure the area of the rectangles, I'm getting extra pieces in here. I'll get something bigger than the actual answer, but it's an approximation, so I'm not expecting it to be exact anyway. But that's the general principle. I have a curve, I want to find the area under the curve between on some interval. I dissect that interval into a bunch of subintervals, and then I use the right side of each interval to extend up and determine the height of the rectangles. I could also use the left hand. So the principle is the same. Here's my curve. Here's A, here's B, and I dissect this into a bunch of intervals. And now instead of using the right side, here's the left side. And notice that in this case, this is an underestimate. It's because the function is increasing, right? So the right side of the function happens to always be higher than the left side of the function. So for an increasing function, the right-hand rule will always give an overestimate, while the left-hand will give an underestimate. But don't think of that as something general. The function was sloping this way would be different. But here, underestimate. Another principle we can use is that of midpoints. And the idea is, maybe I want to get to the answer a lot quicker without worrying about too much overestimation or underestimation. So the idea is I split this guy into several intervals. But this time I take the middle of each interval, and that determines the height. So I can go up here, and that's my first rectangle. And I go up in the middle here, that's my second rectangle. Up in the middle here, that's my third rectangle. In the middle here, fourth rectangle. In the middle, up here. And so that I can do it using that process. You'll notice here though, it gives me like an overestimate on this side but an underestimate on the other side, and the idea is these two kind of balance out. So for this particular kind of function, this one will probably give us a better answer using less rectangles. But that's not always the case, this is just an example. Right, so there are these three ways you can actually set this process up, right, of approximating the area under a curve. Let's get more specific. All right, let's introduce some notation so that we can do this in a streamlined manner. So here's my curve doing whatever it's doing, right? So here's A, here's B. We cut it into subintervals. Going to introduce some notation. We do it in such a way that all subintervals are of equal length. Right? So say we're using n rectangles. Or equivalently, n subintervals. Okay. So I take this interval AB, I cut it up into n equal parts. What would be the length of one of the parts?
Wait, is n one of the parts? Or
No, n is the number of parts there. So there's an interval AB. I want to cut it up into n equal subintervals. What will be the length of each one?
A to B over n? Like the
Yeah, but what's the length from A to B?
B minus A.
B minus A.
Yeah.
So you take B minus A and divide by n. That would be the length of each subinterval. We call this guy delta x. This here is the length of each subinterval. Assuming that all have equal length, that will be the length of each one. There are methods of doing this where you take unequal lengths, but that's beyond the scope of this class. It's too complicated. We're always going to assume we're cutting up into subintervals. They all have equal length or width, right? You'll notice that here, that forms the width of the rectangle, right? And so to find the area of the rectangle, all we need to now do is the height. Delta x equals the width of each rectangle. The height of each rectangle is given by, how would I figure out the height of each rectangle? Yeah?
So if that's f of x, the first one would be f of a plus n.
Yeah, so
If we're using the right hand.
right. So the idea is we, given by the function itself, plugging in the appropriate values, right? The values that you plug in will vary based on the method you're using. Yeah, but the height of these rectangles are determined by the function itself. There's a y value that's going to tell us how tall the rectangle is. So with this sort of setup, this sort of notation, delta x is going to be the width of my rectangles. The height is going to be given by f evaluated at some convenient x point. Now often we write a to be the first x value, that's called x naught, and b to be the last x value, that's called xn. And so what we can have here is something like a, which is equal to x naught, b, which is equal to xn, and in the middle we just number them by x's with subscripts. So this would be x1, x2, x3, x4, etc. Right? Your function is doing whatever it's doing. So this means, if I'm using the right hand, which sometimes we abbreviate by r little n, what do you think the formula for the area would be? Well, it's length times width for each rectangle, and you add all the rectangles together, right? So it's going to be f of something times delta x plus f of another thing times delta x plus, what is the first guy I'm going to put here? Based on how I wrote this. Right, so this is the interval. The left side is x naught, the right side is x1. What would I plug into this? X1. Because that's the x value that's on the right side, and I'm using the right hand rule. So then I move over here. On the right side there's x2. Then on the right side there's x3, then x4, then x5, all the way to the last interval, where on the right side of that interval is xn. So the final point I'm going to plug in is x. There's a shorthand for this. It's uppercase sigma. I don't know if you guys have ever seen that symbol before. But this is when you want to add a bunch of things that look very similar formula-wise, but all you're changing is just like the accounting number. So I can say it's f of xi times delta x, where my I is starting at 1 and going up to n. Right, so then it's x1 plus x2 plus x3 plus x4, right? F of x1 plus f of x2 plus f of x3. It's a repeated form. This is a shorthand for it. It's called sigma notation. It has a name, right? So this is called sigma, but this is called a Riemann sum, named after a mathematician named Riemann. Very prolific mathematician. So I can describe the right-hand endpoints in terms of a Riemann sum. I mean, I'm giving you theorem formulas. I'll give you we'll do a specific example pretty pretty soon, but I just want you to get the idea behind what we're doing. And another way of writing it. Similarly, we can go with the other guys, right? The left hand would be sometimes called Ln. That's just going to be so what are the guys that are plugged into the left hand?
XO, 0,
X naught,
not, yeah.
then X1, all the way up to
Xn minus 1?
Xn minus 1, right? The one right before the last one, right? Because in the left hand, you're taking all the left sides of all the intervals, right? So in the last interval, Xn is on the right side, the left side is what the one you care about. The one right before that is Xn minus 1. So this one you can even think of as a Riemann sum as well. Here your I is going from 0 up to n minus 1 of f of xi times delta x. Okay. We're not really going to use this notation, I'm just showing you just in case you see it anywhere, you don't freak out. It's just a shorthand for writing that. We can also talk about the midpoints. There's a notation for these. So midpoint is when you go in between each interval and you pick the middle guy. Now those guys are called, they're called xi stars. So this would be like x1 with a star in the superscript, and x2 star, this would be x3 star, and so on and so forth. That's just, again, notation. Whenever you see that, it means you're taking the middle one. So that's f of x1 star times delta x plus f of x2 star times delta x all the way up to f of xn star times delta x, where xi star is the middle value between xi minus 1 and xi. Right, so you take the midpoints and you get the midpoint formula. But this is sort of the idea, right? You'll be given a function that I will tell you, approximate the area under this function using 4 rectangles and left-hand endpoints, for example. And what you're going to do is you're basically going to realize that you're plugging in, finding a bunch of y values, multiplying them by delta x values, adding them all together. So let's actually I just want to introduce, let me introduce one more notation that's going to be important. A titular notation. So in theory, what we're doing, remember we wanted area under the curve. In theory, we can find the exact area under F if, what do you think, how will we find the exact area?
You combine all of them.
Infinite number of ends.
Infinite number of rectangles, right?
Oh, okay.
In theory, like, no, we can't actually do it, but in theory, if I could use an infinite number of rectangles, I'd fill in all the little gaps, right? There'll be no gaps left over, because the rectangles would be infinitely thin. So if we use an infinite number of rectangles, i.e., let n go to infinity. So we take a limit, essentially. So basically, we define the area under the graph to be the limit as n approaches infinity. And you can use any one of these sums, because they'll all give you the same answer when you go to infinity. I goes from 1 up to n, f of xi times delta x. So that's in theory. Right? In theory, if you use an infinite number of rectangles, we can find the exact area. So it's like us adding up length times width, length times width, length times width, an infinite number of times. Now there's a notation for this. Whenever that's what we're doing and we're taking an infinite Riemann sum, we label it the following way. There's a weird squiggly little s, very elongated. We write the lower endpoint here, that's the left-hand endpoint, that's A. Or the right-hand endpoint, that's B. We write the function here, and we write dx for the derivative approximation to delta x. Right? Because as long as you start taking limits, you start getting derivatives and approaching closer and closer to something. Right? So that's the notation. An infinite Riemann sum, this is how we denote it, and we call it, this is called the definite integral of f of x. That's one part of the title. The title of this chapter is called Integrals and Antiderivative. This is what an integral is. It is the area under a curve as derived from a Riemann sum. Basically, take a Riemann sum and take it to the infinity. You get what we call an integral, and that integral is a number that represents the area under a curve. There is also an indefinite integral. When a and b are not specified. Where you just have that thing looking like that. Not the subject of our discussion today, we will talk about later. For now, our focus is going to be on the definite integral. And some consequences of it. So the problem is we wanted to find the area, how much space something takes up. We could dissect this problem into finding areas under a curve. And we approached the problem of finding areas under a curve by erecting rectangles and finding the areas of the rectangles to approximate the area under the curve. If we theoretically let the number of rectangles we use go off to infinity, we would get the exact area under the curve. This is called the definite integral from a to b of the function. Let's do an example. We've been doing theory for a while. Let's take a breather and actually crunch some numbers. Because that's how we relax these days. When you're a calc student, we relax and crunch some numbers. Example. And the problem would be phrased similar to this, so I'm going to use probably similar phrasing. Use Riemann sums with 4 subintervals to approximate the area under function x squared plus 1 on the interval 1 to 5. Using, let's do one of each a right-hand endpoints. Like in a test, I probably would only ask you about one of them, but let's do all 3 to make sure we fully understand how they work. B, left-hand endpoints. C, midpoints. In addition, just for part A, tell me if you think is an overestimate or underestimate. Okay, so usually you would have like a question where only like part A would be asked. Use Riemann sums with 4 subintervals to approximate the area under this with this using the right-hand endpoint. So that's all the pieces of information you'll be given. You'll be told for the number of subintervals, that's going to be your n, that'll be the number of rectangles. You're given the function, obviously that's describing your f of x in the forms that we had before. And you'll be given an interval where, of course, the a is your left-hand endpoint, the b is your right-hand endpoint. So that's an example of a problem. The finite case. I'm going to ask you to do it 4 or 5 times. Maybe 4. You can do it 4 times and then you can do it 5 times. It's just getting too tedious at that point. So yeah, let's do part A. Now I didn't ask you to sketch it here, but I'll just sketch anyway, so you can kind of have a pictorial idea of what's going on. It actually looks very similar to our examples. X squared plus 1, that side looks like this. It's just a parabola shifted up 1, but I only care about the right side, so I'm only drawing half of it. And from 1 to 5, I want to approximate the area under this thing from 1 to 5. So I know I'm using 4 subintervals, so I'm going to cut this from 1 to 5 into 4 equal sections. Cut it in 2 and then cut each of those in 2. And so the question is, what is the x-coordinates for these sections? Right? Now it's easy to see between 1 and 5, but let's actually be a bit more systematic here. We can figure out the intersection points by figuring out the width of this thing. Which means, in other words, the first thing you're going to want to do is figure out what your delta x is. And what is delta x here?
5 minus 1 over 4.
Yeah, it's going to be your b minus a over n, which in this case is 5 minus 1 over 4, which is 1. So what that's saying is the spacing of each of these subintervals, the length, the width of each rectangle, is unit 1. So if you start at 1, the next one is going to be 2, and 3, and 4. So you start at the a, and you keep adding the delta x over and over and over and over again until you get to the b. Right? And that's the spacing. Right? So that's your delta x, the spacing here. So that tells you how to fill out these numbers. Now we want to use right-hand endpoints. So the picture for right-hand endpoints would look like this. Okay. So now let's continue. Remember the function expression. So basically part A is asking us about finding R4, right, as an approximation for the area. So we have the area. I'm going to approximate it using R4, right-hand endpoints of R4, which means I'm going to take delta x times f of a bunch of values. In fact, they're going to be exactly 4 values. 1, 2, 3, 4. What are the values I'm evaluating at?
1, no, 2.
2, 3,
2, 3, 4, 5.
Okay, we see why 2, 3, 4, 5? Because our intervals are here. These are the guys we care about. So you look at the first interval, we're doing right-hand endpoints, so it means that the right side is where we're getting our numbers from. So 2 is going to be the first guy you plug in. Move on to the next one, 3 is on the right side. Next one, 4 is on the right side. Next one, 5 is on the right side. So we're plugging in 2, 3, 4, 5. All the guys that are on the right side of every interval. And that's kind of it. Now we just sort of plug in the numbers. Your delta x is 1. F of 2 is going to be 2 squared plus 1 plus f of 3 is 3 squared plus 1. 4 squared plus 1. 5 squared plus 1. And that's your approximation. What's that? 57? 58? I think it was 8. Yeah, okay. So this here is 10, this guy and these two.
Wait, it's 57, I
30.
think.
Huh?
It's 57.
57?
No, it's 58.
That's 58.
Forget these.
So that would be your approximation for the area. Whatever units I'm measuring these axes in, that's the squared units that would be here. So my x and y are measured in inches, it would be 58 inches squared would be my approximation for the area. Overestimate or underestimate? Overestimate. You can tell that by the picture. Clearly the rectangles are covering the curve and more. So overestimate here. C sketch. Yeah.
But, did you say that the right order methods would always be overestimated?
No, they would not. It depends on the situation.
Wait.
Right, because if my function is going like that, then the right side would always give me something that's under. So it depends on the situation. But that's an example. That would be the full problem. So if I ask you, use Riemann sums with 4 subintervals to approximate the area under x squared plus 1 using the right-hand rule from 1 to 5, this would be the answer. Alright, so you figure out your delta x, tells you how to break up the intervals, take the right number on every interval, plug that into your function, multiply by delta x, add them all together. Yes.
Do you add 1, like, to account for the width of the,
This one is to here.
the ones, like, when you add 1 for each of the,
No, that was in the function. The definition of function was x squared plus 1. Yeah, so that's not accounted for the width. This is the f of 2, f of 3, f of 4, f of 5. It's from the actual definition of the function. The width is the delta x. That guy comes on the outside. Similarly, let's do L4. Right? So we still have that interval here where it's 1 to 5, and we have 2, 3, 4. So if we're doing L4, what are the guys that we care about?
1, 2, 3, 4.
1, 2, 3, and 4. These are the guys I'm going to be plugging into the interval. So this is delta x times f of 1 plus f of 2 plus f of 3 plus f of 4. And so we already found this, that's 1. This would be 1 squared plus 1 plus 2 squared plus 1 plus 3 squared plus 1 plus 4 squared plus 1. What's that one? Okay, what if I ask you about midpoints? This is the hardest one, so. Although when you get used to it, none of them are particularly that tough. Yeah.
Can you ever like just take what you got from the left and right, add it together, and divide by 2 to be the midpoint, or no?
It would depend on the function.
That depends on the function.
I mean, in Calc 1 you might have nice functions, but that would be a coincidence, I think. It wouldn't be something in general. Something like that would really only work if the function is like a straight line. But anyway. Yeah, so we're doing midpoints. This is part C. So what do we need to find here? Right, we need to find the middle numbers. Go ahead, color control. So how would we find this one?
1 plus 2 or 2.
Right, so that would be the systematic way to do it. That would be your x1 star. And so that's 3 over 2 or 1.5. Now once you find the first one to be 1.5, notice that the distance between all the midpoints will also be delta x. So I can just from that add 1, so this is 2.5, from that add 1, so this is 3.5, add 1, this is 4.5. Right? So that's my x1 star, x2 star, x3 star. These are the important numbers now, the midpoints. And so this means, if I'm looking at the midpoint rule, evaluating with 4 intervals, this is delta x times f of 1.5 plus f of 2.5 plus f of 3.5. So that would be equal to 1 times 1.5 squared plus 1 plus 2.5 squared plus 1 plus 3.5 squared plus 1 plus 4.5 squared plus 1. And that's equal to whatever. Like on a test, you'd have a calculator, you can just plug it in. Basically how you do it. That's the finite case. Definitely something you'll be asked to do, but you'll be asked to do more than that. Where's the colored chalk? I definitely have those. Any question on this so far?
Wait, so you still have to answer whether you overestimate or underestimate?
I just said that for part A, but in the test I might ask, I might not ask.
But for this one, would it apply for the midpoint? Like
It would be hard to say for the midpoint, because especially depending on the function, part might be over, part might be under, it's hard to tell. So I wouldn't ask that for a midpoint. It would be more like for a right or a left, and where it's obvious, then probably. Some of these are not that obvious. If it's an over or under, or how much is it over by, or how much under it's over by. Usually you'll have to actually find the exact answer, and then you can find the difference. Let's go back to an old example. The same example where I kind of justified to you the idea of the derivative and why somehow the slope could be interpreted as speed. You might remember that example, right? The situation was we're plotting time against distance traveled. And the distance was in miles, and we're imagining some car moving at constant speed, just to make it simple. And we saw that in 2 hours, it traveled a distance of 80 miles. And so that was how we drew it's the function that maps its distance over time. And it was a straight line for simplicity, so you can get the idea of the slope. And we found the slope and we interpreted it as the speed of the car because its units were miles per hour, which is the rate of change of the distance per time. Let's go back to that same example. So you want to graph velocity, which is, it's equal to speed here because it's positive, right? Speed is the absolute value of velocity. Velocity can have signs and negatives and positives. But let's say we wanted to graph the speed here. What would that look like? What would that picture look like? Like I'm graphing the speed over time, the velocity over time. What would that graph look like? What is the speed? Speed is a slope, it's 40. It's also a straight line, so that means it has constant slope. So this is just modeling some situation where there's a car that passes a certain point driving at a speed of 40 miles per hour and it keeps driving at that speed for 2 hours straight. Not very realistic, but it's something that I want you to see in principle. So literally the velocity function would be a constant function, a horizontal line passing through 40. It's always going to be 40 for the entire 2 hours. Right? Now here's a question for you. What is the area under the V graph for 1 to 2, for 0 to 2? Turns out to be the distance. You'll notice that here, if you find the area of this, it's going to be length times width. You'll get 80, right? It happens to be equal to 80. But you'll notice that you can interpret that as a distance. It's actually a change in distance. I can actually make it a little bit more. I can talk about what distance was covered between 1 and 2. And I could again measure this between 1 and 2. And you realize the distance traveled between 1 and 2 was 40. And it turns out that the area in this region is 40. Which seems to be curious that those two will always line up. And so you might wonder, do those two always line up? The answer is yes. It turns out. Something like this. This is always true under some conditions. So we talk about continuity and all sorts of stuff like that. Note what we're saying here. To use the symbols that I introduced since this class, what I'm saying is the area between 0 and 2 under the velocity graph is actually equal to the distance traveled between 0 and 2. Measure the distance, my position at 2, measure my position at 0, find the difference between them, that's how much distance I've traveled. It turns out that's always the same as the area under the velocity graph. It's not a coincidence. I mean, it's a simple example, and I chose it so you can see the numbers, but it's actually not a coincidence for that to happen. Something like this actually happens a lot. And in fact, it's very poetic that I use the exact same example, because that's the thing that it's going to reveal to us, is that there are two things that are related that you might not have thought of being related, and that is speed and area. Right? So it turns out that I can talk about the area under the speed graph, and somehow that I can look at the same picture and sort of get both pieces of information by just looking at the flip side of the problem. Also note here, so I'm using S here to represent my position function. What is V? Remember we spoke about what S and V and A are? What is V?
Derivative of...
It's actually the derivative of S. Right? That's how we get to velocity. Which means to go from here down here, I would differentiate. But there are some problems where I can be concerned with this graph, and the answer leads me back to that graph. For example, if I'm considering the area under one. So it turns out that sometimes we can actually reverse this process. And the reverse of this process is called anti-differentiating. It's called the anti-differentiating. In other words, saying V is the derivative of S is saying S is an antiderivative of V. You can think of it from the other way, right? Let's say I anti-did what I did before, anti-differentiated. I'm going to define it in general, then make an important conclusion. Without proof, it's actually not that hard to prove, but I'm not going to prove it. Unless, if you guys want to see the proof, I can show you next time. It will take like 5 minutes, but I'm never going to ask you to do it. So, here's the definition. Suppose f of x is a differentiable function, meaning you can differentiate it such that when I take its derivative, I get another function, f of x. Right? I'm going to define the phrasing of that function. Then f is called an antiderivative of f of x. Right? So in a similar way, s was a function that when I differentiated it, I got v. I can say f is the antiderivative of v. Right? It's just the thing I get by reversing the derivative. And that's the other name in the title of the chapter. Right? So the chapter is entitled Integrals and Antiderivatives. I told you what an integral was. It was the area under a graph between two intervals, and the antiderivative is just the reverse of the derivative. And what I just kind of showed with this example is that these two are connected. The area under a graph is connected to somehow reversing a derivative. Here's the conclusion with some work, not shown. Is that if f of x is continuous, and f of x is an antiderivative of f of x, then the area under the graph of f of x from a to b will be equal to big F evaluated at b minus big F evaluated at a. Yes?
Just to clarify, if f prime of x is the same as f of x, then f of x would be an antiderivative of itself. Because
You're saying if they're the same, f prime
Yeah.
of x is equal to f of x?
yeah.
Yeah, then it will be an antiderivative of itself. Which is possible. For example, the function 0 satisfies that, so does e to the x. So that wouldn't be strange. But in general, these aren't the same functions in general. Big F and little f are.
But then on the bottom, like, did you need to write f of x is called an antiderivative of x, or is that supposed to be f prime of x?
No, I meant that.
Oh,
So-
that's only if there's
So
something-
the example here is take big f of x to be a position function and little f of x to be the velocity function. Right? This guy is the derivative of that guy. Right? So this guy is the antiderivative of that guy. Right? So to go from v up to here, it's also true that if I take f prime, I would get v. Right? So the big F is the guy that's called the antiderivative. And it turns out that we can talk about the area under curves by looking at the antiderivative of the curve. Right? Evaluate at the endpoints, I get the exact area under the curve. And I know it's a strange thing to say when you're saying it in words and you're like, what? How the hell are these two connected? But when you do the algebra behind it, it's like super easy and straightforward. Like, well, that's interesting how that works out. But this is true. And in fact, it's a very, very important equation. You must memorize it. Because it's super important equation. I mean, next to the equation of the definition of derivative, this is the most important equation in the entire course. So important that, look at its name, not modest at all. It is called the Fundamental Theorem of this chapter. No, of all of calculus. It's that big of a deal. Noticing this is that big of a deal. The study of modern calculus as it is studied today is because of this fact. It's one of the facts. This is one part of it. Right? It comes in two pieces. There are two pieces of information that are in the Fundamental Theorem of Calculus, but this is one of them. It tells you about the relationship between the area under a graph and the antiderivative of the function that you're considering in the first place. It's the Fundamental Theorem of Calculus. And I mentioned this like before in one of the first lectures where I told you that, individually we're doing little pieces of calculus here and there all over the place, and the reason why Newton and Leibniz were credited with being the fathers of calculus is because they kind of stitched all this together. It's because their work was instrumental in coming up with this theory. The fact that, this idea of finding areas and the idea of finding a derivative, they're actually connected in some way. Like these two separate schools of math, they're actually not separate at all. Right? And it's very odd when you think of it in terms of what it means in physical reality. It's a very weird thing to say, but in terms of the math, it checks out. It checks out all the time in all cases. And they can prove this in general, that this is always true under these conditions. If an antiderivative exists, we can find the area under the curve by doing this manipulation. And it turns out it's connected to a derivative, which is very, very strange. So it turns out the area problem and the rate problem are actually two sides of the same coin. It's the same problem being solved from different ends, right? And noticing that makes calculus. That's why you're here today. Someone noticed this, and that's why you have to study it now,
That's
right? Because it's that important. The applications that come out of this, it's unbelievable. Look at what we did in this class just by figuring out the slope of a straight line. Using the slope of a straight line, we did like optimization, we did related rates, we could find all sorts of stuff. How fast is this changing? How fast is that changing? When is this a maximum? When is that a minimum? Look at all the things that came out of the slope of a straight line. It turns out knowing about area also has many applications. There's a lot of things that just get a lot out of it. And then realizing that those two things are connected. So that means if we're studying one thing, and we get stuck, we can kind of flip the script, go over here and get further, and then we can kind of interplay these two schools of math and build all sorts of crazy things out of it. So it's a very important theory, that the area and the derivative are connected. It's called the Fundamental Theorem of Calculus. Let's talk a little bit more about antiderivatives. Of course, we're not going to see all the amazing things. I mean, that's what Calc 2 and 3 are for. That it's basically studying the consequences of this. And you can get like 6 more calculus classes out of studying it. But we're in Calc 1, we're just doing this at the end, just so you can know it's out there. But to study it, you need more calculus classes. More on antiderivatives. I don't know if you noticed. I pretty much always wrote an antiderivative. In other words, I never said the antiderivative. That's because an antiderivative of a function is not unique in general. A function can have many antiderivatives. So for example, let's look at an example. What is the antiderivative of 2x? Okay. So that's me asking you the question, what function did I differentiate in order to get 2x, right? So I want you to anti-differentiate this function. Something was differentiated to give me 2x. Find the antiderivative. Find the original guy that came from. X squared.
Wow, I'm so smart.
Yeah, well, you guys have found the derivative of x squared like thousands of times in this class so far. So yeah, you can get that one, not with too much work. But is that the only answer? Can you think of another answer?
X
X
squared
squared
plus
plus
X squared plus 1 is also an answer. Because when I differentiate a constant, I get 0. X squared plus 17. X squared plus pi. There is an infinite number of antiderivatives to 2x, right? Why? Because when you differentiate a constant, it goes to 0 and you don't get it. So it turns out antiderivatives, they will differ. Any function that has one has an infinite number, and they will differ by a constant value. So that is the antiderivative of x squared of 2x is x squared plus c. And we write this to mean, we write a plus c to indicate that for any arbitrary constant, this will be an antiderivative. Right? Because there could have been a constant there that when I differentiated, it disappeared. And so I don't see it now, but it could have been there. So you kind of put a placeholder. When you say this is the antiderivative of x squared, the antiderivative of 2x, it is x squared plus some constant. Potentially there was a constant there that died. Tragically. In a bees. They're not gonna know. They won't know. Come on.
Yo, that's fun.
Let's go.
You should have been here earlier. There was a whole
Don't blame
thing.
it on us. You're the one who made the joke in the first
What?
place.
No, it was them.
Oh, really?
Oh no.
Those two. You should have heard them. You should have heard them when you were in
It's
here.
messed
Okay.
up.
It's like the artist out.
Anyway, that is the antiderivative of 2x. Okay. Now it turns out. Okay, we're almost done. So it turns out that for 2x, you knew the answer was x squared because you've seen it so often. But was there a streamlined, more sophisticated, formulaic way to say it? Yes, the answer is yes. By the way, in this case, because the antiderivative and the derivative are connected to the area, you can actually use a similar notation. In this case, we write of 2x dx equals x squared plus c, right? And notice I write an indefinite integral. So I don't specify what interval I'm working on. I'm just specifying in general the antiderivative of this function is that function. But to get from taking the derivative of x squared to 2x, we had to use the power rule. Therefore, it suggests we can reverse the power rule. Which is a right, there's a systematic way for us to turn a polynomial into its derivative. There should be a systematic way to go from some other polynomial to its antiderivative, right? If there's a nice formula to go in this direction, there should be a nice formula to go in that direction. Just reverse the formula, solve for the other guy, right? So, and it is the following. So let's say I want to take the antiderivative of something to a power dx. What do you think the answer would look like? Try to think of what it would mean to reverse the power rule for derivatives.
It would be like n plus 1 or something.
Right, so in the derivatives, from the original you ended up subtracting a power, so why not add 1 to the power? Because we ended up subtracting 1 from the power. And divided by n plus 1. Notice that here, right, I divide by the old power because we multiply by the old power. So n plus 1 represents the old power. So to get rid of the multiplication by that power, we divide by that power. And this will work as long as n is not equal to minus 1, of course, because we're always worried about dividing by 0. So this is a rule, and this is the first rule that we have for antiderivatives or integrals. We'll use those names interchangeably now because of the fundamental theorem of calculus. So if I say integral or antiderivative, I'm talking about the same thing in general. So this leads us to the first rule. This is called the power rule for integrals. And we'll stop there because that's where I stopped in my last class. So I believe we actually completed 5.1. The fundamental theorem of calculus, I think they spoke about in 5.2. So we actually started 5.2. So we didn't finish it. I'll give you some more examples here, but 5.1 we finished. So I'll see you guys on Tuesday, and we'll